All right, folks, back here with another video, right? We're looking at derivatives, and we're getting close to the end here, folks. We have almost looked at every single case for differentiation. We have just a couple more function types to talk about. I only have a couple more lecture videos focused specifically on types of functions and their derivatives. The one we're going to talk about in this video is the case for the derivative of the exponential and logarithmic functions in general. All right. What's the derivative of the function 3 to the x power, for example? All right. There is a derivative rule associated with that. Or what is the derivative for the log base 4 of x? Right. There is a derivative rule for that case, and we're going to look at those rules in this video. All right, folks, so that is where we're heading with all of this. Let me bring up my notes here. Where we actually begin, though, right, is we just take note, right, of something we already understand. And that is, right, for the function f of x equals e to the x, right, the derivative with respect to x for e to the x is also just equal to e to the x. That's a fundamental derivative rule that we developed earlier in our notes, right? I have a whole video devoted to that topic, right? And we defined e and we proved that derivative result. What we're now going to begin with considering is the derivative for its logarithmic counterpart, right? The derivative for the natural logarithmic function given by the ln of x, which is the log base e of x, right? If you remember, these two functions are what we call inverses of each other. When composed with one another, if I take e to the x and I compose it with log base e to the x, or the ln of x, the two undo each other in their composition, right? They are inverse functions with one another. And the way we're going to go about finding the derivative is we're going to exploit that inverse behavior along with what are going to be some implicit techniques. Right? We are going to look at some implicit techniques as we examine this inverse behavior. All right, let me bring this into view. To begin with, what we note, and this is a fundamental idea that we use to define the logarithmic functions, and that is using their relationship with the inverse of the exponential. And what we start by noting is that y equals the ln of x if and only if x is equal to e raised to the yth power. Right? Remember from college algebra, how we define logarithms is based upon their inverse relationship with an exponential function of a similar base. Here, for the natural logarithmic function ln of x, it is in this inverse relationship with the function e to the x. So what we can say about y equals the ln of x is that x inside of here must be equal to e raised to the power of y. And that's how we define the natural logarithmic function. Now, if we apply d dx to both sides of this result, that implication, that result from the if and only if for y equals the ln of x, if we apply it to both sides of x e to the y, applying it on the left, we can see that does yield the value of 1. But when we apply it on the right, because our function is not a function of x, we have to use those implicit techniques and note that the derivative with respect to x for e to the y is actually y prime the derivative times the derivative with respect to y for e to the y, where from the above result with respect to x, we know that is also just equivalent to e to the x. Or, well, for e to the y would be e to the y. All right. So what we're able to say is that 1 must be equal to then the value of y prime times e to the y, or y prime must be equal to the result of 1 over e to the y. Right? Y prime being the derivative of y equal to the ln of x. Now, what you do notice is that y inside of e to the y is equivalent to the ln of x in our opening statement. And since y equals the ln of x, we can substitute that back in there, and with the inverse behavior of an natural exponential function and the natural log, they undo each other in their behavior, and we're left with just the value of x after that substitution, letting y equals the ln of x. So for the natural logarithmic function, we get the result that the derivative of y with respect to x through these techniques is just equal to the result 1 over x. And we can say that in the following theorem. This is called the derivative of the natural logarithmic function. Right? And what it states is if you have the function f of x equals the ln of x, that's your natural logarithmic function, then what is true is that the derivative with respect to x for the ln of x is just equivalent to 1 over x when it is the case that x is greater than 0. Or, and this is incorrect, let me correct this, not equal to. For the case where x is not equal to 0, you could be interested in the derivative with respect to x for the ln of the absolute value of x. And that also is equal to the value of 1 over x. The derivative of the ln of x is always equal to 1 over x. The difference here between these two statements is that this statement allows for x in the logarithmic function to be positive or negative, and not allowed to just be the value of 0. Whereas if you don't have that absoluteness, x will always have to be greater than 0 when considering the ln of x. That's the only difference between these two results. Now, if we put that into an example, we might consider finding y prime for x times the ln of x. And that is a little bit of product rule. Right? It's going to be the derivative of x times the ln of x, so that's going to be 1 times the ln of x, plus x times the derivative of ln of x, which is going to be 1 over x. So x times 1 over x is just going to yield 1. And we're going to see that in our result. From product rule, we're going to have the derivative of x times the ln of x plus x times the derivative of ln of x. And we know the derivative of x is just 1. So the first term is going to be 1 times the ln of x. And we know now the derivative of the ln of x is 1 over x, so in the second term we'll have x times 1 over x, which will just be equivalent to 1. And in the end, the derivative of x ln of x is just equivalent to ln of x plus 1. This is the derivative of x times the ln of x, right? We might even just make quick note of that here. Thus, the derivative with respect to x for x, f4 dot the ln of x is just equal to the ln of x plus 1 in value. All right? And we can draw that result from, and let me highlight that that is y prime. Right? That is the derivative result for this function y equals the value of x times the ln of x. Just a quick example using that derivative of the ln of x result and a little product rule. Now, what can we do with this? Well, if we want to generalize to every logarithmic function of base b and consider what is the derivative in those cases, what we want to consider applying is what's called the change of base theorem. All right. recall the change of base theorem, which allows you to talk about any logarithm of base b in the context of any other base in the form of this ratio, where we have the log of any base of x over the log of any base for what would be the argument of b, the b value being the base from the original logarithm. Since we can use any base, we can use the ln's base, the base of e, and consider that the log base b of x is simply, from the change of base theorem, the ln of x divided by the ln of b. Or if we want, we could even say that this is equal to 1 over the ln of b, because that is going to be a constant value, times what's going to be the ln of x in our result. So if we apply the derivative operator to that result, right, this 1 over the ln of b being a constant multiple, right, can be factored out of that derivative operation, and we're left with, in fact, let me bring this in, because I think this will be a little nicer to say than this. We know that where that comes from is the above, right? That ln of b can be brought out in front as a constant multiple times this derivative operation, where we again know that that derivative operation is equivalent to 1 over x from the derivative of the ln of x function, right, that we developed at the beginning here. So what we have is 1 over the ln of b times 1 over x, which can be simplified into 1 over x times the ln of b. And thus, the derivative for a logarithm of any base b, which is what we're saying here on this left-hand side, is equal to 1 over x times the ln of that value b, the value of the base of that logarithm. And we can state this in the form of a theorem similar to that of the natural logarithmic function, right? Where the derivative with respect to x for just the log base b of x is 1 over x ln of b, and if we consider it for the log base b of the absolute value of x, right, this is equivalent to 1 over the absolute value of x for the ln of b, right, in its result. Give me 2 seconds to think about that for a moment. Yeah, I think I have something. I got a let me think about my statement there. I do think I have an error. Let me reconsider that for just a moment. All right, folks. No, I figured it out here. That didn't take me too long to see what I had done wrong here. Again, it's based upon what x can be here, folks, inside of this function for the logarithm. If you remember, x in a logarithm always has to be greater than the value of 0. Now, what this case considers is forcing x to be greater than 0 by taking its absolute value before the logarithm. So it allows for x to be not equal to 0 in the case of the log base b for the absolute value of x as our functional behavior. In either case, they both result in 1 over x times the ln of b, right? We are going to have negative slopes on values for x less than 0 on this function seen here. All right. So we have to allow for that. We can't have the absolute value of x down here in the denominator, right? I don't know what I was thinking there, but I'm glad I'm going through these because I can spot some of those mistakes, right? So, yes, let's fix that. Now, if we go down and look at an example, here I'm going to throw this into a little bit of quotient rule, right? For the case of log base 3 of x divided by x squared plus 1, right? We might be interested in the derivative for the quotient of those two functions, the logarithm divided by the quadratic. And here I'm going to use the absolute value of x in this statement, which just means x cannot be 0 in this argument, and it also, well, it's allowed, it can be anything else because there's no limitation in the denominator. Now, if we consider applying a little quotient rule, we know the denominator, first of all, is going to be x squared plus 1 quantity squared. It's going to be our denominator of this function squared in the denominator of our result from the quotient rule. Then it is going to be the derivative of the numerator, that logarithm argument, times the quadratic in the denominator, minus the logarithm in the numerator, times the derivative for the quadratic in the denominator. Now, when we go to prepare this, I'm going to go ahead and bring the 1 over x squared out in front because this is going to help simplify this argument, because the derivative of the logarithm is going to be 1 over the absolute value of x times the ln of 3. So we are going to end up with this first term becoming a fractional value given by x squared plus 1 over the absolute value of x times the ln of 3. And that's all going to be minus over here. The derivative for x squared plus 1 is just 2x, so that will be minus 2x times the log base 3 for the absolute value of x. Now, written like this, let me see what I do here. There really is no simple form, folks. You can see what I do here is I go ahead and cancel. Right? If I redistribute this in to the first term, it will cancel with that numerator, so it'll leave one of those quantities of x squared plus 1 behind. But then when it distributes to the second term, we'll still have in the denominator the quantity x squared plus 1 quantity squared. Is that the simplest form? Not necessarily speaking, right? But it is certainly simple. I mean, we can see where we could go from here if we wanted to write it as a single rational value also. All right? But in the end, what we do have is the complex functional relationship that describes the slope of the lines tangent to the curve given by this complex functional relationship. Right? And if we were interested in the slope tangent at any value of x other than 0, we would, right, be able to calculate that with this calculation seen here. Right? And maybe we should finish this one by saying, thus, the derivative, or we'll go back, we'll note this is going to be y prime, which is equal to the derivative with respect to x for the log base 3 for the oh, I got to fix my answer here too, because what do we know? This is just x. This isn't the absolute value of x. Again, that was an error in my thought process there for some reason or another. So this is going to be, excuse me, x squared plus 1 is going to be equal to the above result. We'll just capture that. Bring that down here, put that in. All right. And we can draw that conclusion. Let me clean up the absolute values in there for that value of x. All right. Now, there is one last situation we have to go back now and consider. We've looked at the derivative for the natural exponential function e to the x. We've looked at the derivative for its logarithmic counterpart, the natural logarithmic function. And we've looked at the derivatives for just logarithms of any base b. What we now need to go back and look at are the derivative results for just derivatives of exponential functions for any base. And that's what we now consider. And we do see similar techniques applied to what we've done above for the case of finding dy dx for f of x equals b to the x power. We use some of those implicit techniques and a little bit of knowledge about the inverse relationships. Right? We can note y equals b to the x if and only if x equals log base b of y. So if I take that x equals the log base b of y and I apply the derivative operator to both sides, I'm going to give myself this result here where I know on the left-hand side that's going to become the value of 1. And on the right-hand side, because I do not have a function of x in my argument here, I then have to write that as y prime times the derivative with respect to y for that function now of y. Right? This log base b of y. When I consider that derivative following the logarithmic rule, we know that's 1 over y ln of b. If we bring that up, so we end up with 1 equals y prime times 1 over y times the ln of b. And if we solve this for y prime, multiplying both sides by y ln of b, we end up with y prime equals y ln of b. Or what do we know about y? Y is b to the x. This value of y right here is equal to the value of b to the x, so we can substitute back in for that value. And we're able to say y prime is equal to b to the x times the ln of b. Right? And this becomes our result for the derivative of an exponential function with any base b. Right? If we bring that result in, right, we can say thus, the derivative with respect to x for b to the x is just b to the x ln of b. And if we say that in the form of a theorem, we might say it this way. Right? Where we clearly identify what function we're looking at as the exponential function, where b is its base. It has to be greater than 0 and not equal to 1 in this setup. And the result is b to the x ln of b for that base of x. If we look at a quick example, and we'll finish with this example. Okay. We might consider finding y prime for y equals 5 raised to the x squared power. Well, here's a little chain rule in this example. I could let u equal that x squared, and y would then equal 5 to the uth power. And du dx would be equal to then 2 times x. Right? If I take the derivative of u with respect to x for x squared, that would be equal to 2 times x. Let's highlight that that's where that derivative is coming from. And if I find then the derivative of y with respect to u, which would be the derivative with respect to u for the quantity 5 raised to the uth power, well, that would be 5u ln of 5. And from the chain rule, dy dx would be dy du times du dx, which would be 5u ln of 5 times 2 to the x, where we know the value of u, again, is just equal to x squared in value. So we can substitute that in there for that value of u. And in the end, we end up with 2 to the x times 5 to the x squared power all times the ln of 5 as our result. Right? That becomes the derivative result in this case. Right? What would be the derivative with respect to x for 5 raised to the power of x squared? Well, that would be 2 to the x times 5 raised to the x squared power times what would be the ln of 5. This would be that derivative result. And we used here the derivative result for the exponential function of base 5 in the context of u, because the problem was setting itself up with a little chain rule. All right. Folks, that is 3 derivative results. The derivative of the exponential function here, of base b, right? The derivative for the logarithmic function of base b here, right? And the derivative result for the natural logarithmic function of base e here, to go along with the derivative result for what is, we already understand, is this the derivative of the natural exponential function. Right? And really, if you think about it, the natural exponential function is just a specific case of the rule we just developed. If we go back down to the end here, this rule that we just developed, The natural exponential function is just a specific case of b. It's just the case of b is equal to e. And if I substitute in the value of e here, and I substitute in the value of e here, well, the ln of e, is just equal to the value of 1. So this would be like multiplying by 1. And what is e to the x times 1? Well, it's just e to the x. And that's where we get our derivative result for e to the x. That's how we can, well, we can see that that result is supported by this derivative rule. Let me back out of there. Ooh, and that's going to be b to the x. And this is going to have to be back to a b. All right. A similar result can also be shown for the logarithmic of base b up here. All right. In the case of the natural logarithmic function, that is a base e. All right. Where this ends up becoming the ln of e, where again, what do we know about the ln of e is that that's equivalent to the value of 1. So you have in the denominator x times 1, which is just equivalent to the value of x. So the log base e of x, or the ln of x, is also equal to just, its derivative is equal to 1 over x. And this logarithmic rule of any base supports that result for the natural logarithmic function also, a base e. Now let me back out of here. I'm going to have to put the b in here. All right. So folks, that is a set of rules for those cases. Those cases, the logarithmic and exponential functions, to go along with our derivative results for the natural, exponential, and what we started with was the natural logarithmic function. That is another set of function types related through their inverse behavior, where we now have a set of rules to tackle those cases for functions. There's one more case that we got to get into, and we got to, I think, talk about the inverse trigonometric functions and their derivative results. And their derivative results are going to develop very similar to what we did here with that inverse behavior. But that's for the next video, folks. So I will end this one here, and I will see you in the next one.